In this video, you will learn step by step how to build fully functional agentic AI for industrial systems, from the very basics to advanced multi-agent architectures. This video is divided into 5 parts. In part 1, I'll walk you through how to build an industrial AI agent from scratch using Python, LangChain, Claude LLM, and 2 key data sources, an OPC UA server, and TimescaleDB database. We'll begin by creating Python functions to access data from OPC UA and TimescaleDB. Then we'll expose these functions as tools that the AI agent can use. Finally, we'll use the LangChain framework to build a batch-planned production assistant AI agent that can reason over your industrial data. In part 2, I'll show you how to run your AI agent locally at the industrial edge. We'll take the AI agent we built in part 1 and replace its cloud-based Claude LLM with a locally hosted model using Ollama and Mistral. In other words, we'll swap out the brain of the agent with a local LLM, enabling fully offline on-premise AI capabilities right at the edge. In part 3, I'll show you how to build an Agentic RAG or Retrieval Augmented Generation pipeline for industrial data. This means extending the AI agent we built in the earlier parts to include unstructured data sources like maintenance documents into its reasoning process. I'll walk you through deploying an embedding model at the edge, storing vector embeddings of your documents in a Chroma vector database, building a semantic search function, and exposing these embeddings as additional tools your AI agent can use for richer context-aware responses. In part 4, I'll show you how to build a model context protocol or MCP server for industrial data. This involves taking the custom LangChain tools we previously created for our AI agent and replacing them with standardized MCP server tools. These standardized tools can then be accessed by any AI agent. In part 5, I'll show you how to build a multi-agent industrial AI system using the agent-to-agent or A2A communication protocol. This means breaking down our monolithic AI agent into several specialized agents, such as an equipment monitoring agent, a material calculating agent, and an orchestrator agent responsible for delegating tasks across the system. We will then implement the A2A protocol, enabling these agents to communicate, collaborate, and share context, laying the foundation for a distributed, intelligent agent ecosystem in industrial environments. To make all this concrete, I'll be using a simulated batch plant as the demonstration environment. The plant includes 3 storage tanks for raw materials, a mixer that blends materials based on a recipe, a reactor for executing the chemical process, and a filler that packages the finished product. All real-time signals from this equipment are exposed via an OPC UA server, and a TimescaleDB database stores product definitions and recipes. All the code used in this video is available on the GitHub link in the description below, so you can follow along. My name is Kudzai Teresa, and I regularly publish tutorials on industrial data and AI right here on this channel. So if you're new here, make sure to subscribe so you never miss any of the upcoming videos. Now let's get started. We'll start by exploring the simulated batch plant environment we'll be working with, and then step by step, I'll show you how to create Python functions to access data from an OPC UA server and a TimescaleDB database of our plant, expose those functions as tools that the AI agent can use to make intelligent decisions, and then use Claude large language model to build a LangChain tool calling AI agent. Before we dive in, let me show you a quick demo of the finished project, and then we'll go through exactly how to build it. So here I've built a batch plant production assistant AI agent. It can assess whether to proceed with production based on material availability in the tanks, equipment availability, and product recipes stored in our database. Now here's a hypothetical scenario. Now imagine you're starting a production shift. The main question is, can we successfully produce X batches of product A? Traditionally, you'd have to manually check raw materials in the tanks, walk over to each machine to verify its status, and cross-reference recipe information. This process obviously is slow and it is prone to error. Our goal is to automate this. We will build an AI agent that lets us ask in plain English, do we have enough resources for X batches of product A. The agent will then connect to our factory's data systems, gather all the necessary information, provide a clear go, no go decision, and then explain why it reached that conclusion. While this is a simplified scenario, the principles you will learn here are the foundation for tackling much more complex industrial problems. Now let me show you what we're working with here. So I've set up a simulated batch plant that's actually pretty representative of what you'd find in a real facility. We have 3 storage tanks that hold our raw materials, a mixer that combines these materials according to our recipes, a reactor where the actual chemical processing happens, and finally a filling machine that packages our finished product. And we're exposing all the real-time data from all our equipment using an OPC UA server. Now let me show you data from the OPC UA server of this plant simulation. And to do that, I'll use my process OPC UA browser to connect to my simulated plant OPC UA endpoint. And you can see here we've got the live value for silo or tank level 1 showing exactly how much material is in this tank, and same applies for tank 2 and tank 3. And we also have equipment states. So here you can see this is my mixer state, which is an integer that tells us whether each machine is running, idle, or down for maintenance. Same applies for the reactor and the filler. Next, we have a TimescaleDB database that stores static product information. We've got 3 key tables here: a products table, a product recipes table that tells us exactly what materials we need for each product, and a raw materials table. Okay, now that we understand our environment, let's build an AI agent to interact with it. Before we can build the AI part of our agent, we need simple Python functions to communicate with our data sources. Think of these as the agent's basic senses or capabilities. So now I'm on my Visual Studio Code here. I have a Python script called batch plant functions that acts as our OPC UA client. As you can see, it uses the async UA library to connect to the server. It defines the server endpoint and the specific node IDs for our tank levels and machine states. And it has 2 key functions: get material availability, which reads and returns the current levels of tanks 1, 2, and 3, and get machine states, which returns to us the operational status of each piece of equipment. Let me run the script so you can see it in action. So as you can see, we're getting live readings from each tank, and we can see the operational status of our mixer, reactor, and filler. And if you notice here, I have an enumeration to map our machine states to these descriptions. Now the second script is called batch plant storage, and this one reads data from our TimescaleDB database. The key function here is get product details, which takes a product name and returns exactly how much of each material we need to produce one batch of that product, plus it tells us which tanks contains those materials. Now let's test it. And as you can see, it returns the required materials and which tanks they come from. Now that we have verified our data access works, let's talk about how our AI agent is actually going to function. Now think of this as a smart pipeline that processes information step by step to reach a decision. Here is how that workflow operates. First, you give it a natural language input, which contains the number of batches you want to produce and the name of the product. The agent then queries the database to retrieve the recipe and figure out the total material requirements. Next, it sends a request to the OPC UA server to check material levels in each tank and verify that all our machines are available and not down for maintenance. Finally, it compares what we need versus what we have and makes a decision, giving you a clear go or no go answer with detailed reasoning. Now, at the heart of this system is a large language model, and we are using Claude from Anthropic for this tutorial. The LLM acts as the brain, interpreting your natural language input and orchestrating the entire workflow. But here's the thing, Claude or any LLM doesn't naturally know how to talk to OPC UA server or databases. That's where our Python functions come in. We're going to transform them into tools that the LLM can call whenever it needs to retrieve data. And critically, we need a prompt template that gives the agent clear instructions about its role, what tools it has available, and how it should behave. This is what ensures we get consistent, accurate responses every time. All right, let's start building the agent. First, let me show you the libraries you will need. So you will need LangChain Anthropic for Claude integration and LangChain Community for the core LangChain tools. We're still using async OPC UA and the PostgreSQL library, and I'm also using Pydantic, which is going to help us format our outputs in a really clean way. Now, LangChain is a framework that's specifically designed to simplify the development of LLM-powered applications like the agent we're building. So it's going to handle a lot of the complexity for us, which means we can focus on the actual functionality of our AI agent. So the first step in building our agent is to convert our Python functions into tools that the AI can use. So I've created a file here called tools.py for this purpose. What we're doing here is importing our batch plant functions and batch plant storage scripts, and then using LangChain's tool class to wrap them. Each function becomes a tool with a clear name and description that helps the LLM understand when and how to use it. LangChain tools expect synchronous functions, but our OPC UA functions are asynchronous. So I've created synchronous wrappers that handle this conversion. You might not need this if your data access functions are not async. And as I have discovered, LLMs sometimes try to pass arguments to tools that don't need them. For example, our OPC UA methods don't take any arguments, they just return current values. So I have added args and quags to the wrapper functions to gracefully ignore any unexpected arguments the LLM might try to pass. Okay, so now for the main application. Now in my main file, I start by importing all the necessary components. I'm using base model from Pydantic to define our output structure, chat Anthropic from LangChain Anthropic for our LLM, and various prompt and passing utilities from LangChain. The key imports here are the tool calling agent from LangChain.agents, which gives us an agent with built-in ability to call tools, and agent executor, which actually executes the functions since the LLM itself just provides instructions on what tools to call. Next, I define exactly how I want my output structured using Pydantic. So as you can see here, I want a clear decision, yes or no, detailed reasoning explaining that decision, the actual material availability data, machine states, and a list of which tools were used. This structured output makes it much easier to use the agent's response in other applications. And then here I create an instance of chat Anthropic, specifying that I want to use a specific version of Claude. You will need to get an API key from Anthropic and add it to your environment variables for this to work. Now comes the really important part, which is the prompt template. This is where we give the agent its instructions. We tell it exactly what its job is, which is to determine if we can complete a production run. We explain what tools it has available and what each one does. We specify the format we want for the output, and we include any special rules or edge cases it should handle. After setting up the prompt, I put all our tools into an array and create the actual tool calling agent, passing in the LLM, the prompt, and the tools. And then I wrap it in an agent executor, which is responsible for actually running the functions when the LLM decides they need to be called. And then here I'm just extracting the JSON from the response. And then here on my main function, I'm going to prompt the user to enter what product and number of batches they want to produce. And then I run the agent, extract JSON from the response, pass it into our Pydantic module to structure the response nicely, and then print out the response. So now let's go ahead and run our complete AI agent system and see the response. Okay, so as you can see, the agent has given us the response. So let's go through it. So as you can see here, we've got the production assessment results. First of all, the decision, yes, you can produce 3 batches of product A. And then we've got the reasoning here. For 3 batches of product A you need, and then it does its calculation, how much of material is required, how much material is required for the product. And then it says all materials are sufficient and all machines are operational, none in fault state. So sufficient materials is true, and then it gives me the machine states. We've got the mixer state running, our reactor is currently idle, and then we've got the failure state, which is also running. And then it also gives me the material availability. You can see here we've got the tank 1 material 1 level, 8,000. We've got the tank 2 material level, 13,000 and 32,000. And then if we check with our ignition SCADA system, you can see that it's actually giving us an accurate indication of the current availability of the materials. Now, the AI agent we just built works, but there is a catch. It's entirely dependent on the Claude large language model, which is hosted in the cloud on Anthropic's servers. And for some industrial use cases, that's not ideal. Concerns around cost, data privacy, and latency often require these systems to run locally at the industrial edge. So in part 2, I'll show you how to deploy a local LLM on your own hardware and run the entire AI agent system within your environment. So here's what we're going to do. Instead of using Claude as the LLM, we're going to replace it with a local model that runs entirely on our machine. And the nice part is we're going to reuse for our existing code. The data connections stay the same, the tool definitions stay the same, the agentic logic stays the same. We're literally just going to swap out the brain. So how exactly do we run large language models locally? We're going to use a tool called Ollama. Think of Ollama as Docker, but specifically for AI models. It handles all the complexity of running these models, managing resources, and providing APIs. Ollama is completely free and open source, and it runs on Windows, Mac, and Linux. So let's get it installed. Okay, so now that Ollama is installed, we can verify the version. Okay, so Ollama is successfully installed and we're ready to go. Now the next thing that we need to do is to choose a model to deploy on our hardware using Ollama. So when you go to ollama.com/library, you'll see a comprehensive list of available models. Each model has different characteristics, different sizes, and different capabilities, which obviously means different hardware requirements. Now the type of hardware you have will dictate which models you can run effectively. In my case, I'm going to download the Mistral 7 billion parameter model. And to do that, I'll go to the terminal and type in the following command. Okay, download is complete. So let us verify if it's working by running Okay, let's just ask a simple question. Okay, so we've got a large language model running entirely on our machine. All right, let's modify our code to use Ollama instead of Claude. First, we need to install LangChain Ollama. And then we import chat Ollama from LangChain Ollama. And then next we find where we instantiated the Claude model, which is this line here. And then we replace it with the Mistral model. Okay, now we don't need to change our tools, our prompt, or anything else. LangChain abstracts away all the differences between the models. Our agent should work exactly the same way, just with the local LLM instead of a cloud LLM. Okay, so let's run our locally powered agent and see how it performs. Okay, so as you can see, we've managed to actually get a response from Mistral, which basically gives us the output, but it's sort of like struggled with the structuring, which needs to be adapted specifically for Mistral. So as you can see, we've got the reasoning here. To determine if we can proceed with producing 4 batches of product A, let's first gather the necessary information, and then it goes off and does the calculation. And then here it says the decision production can proceed. Enough materials are available in tanks 1 and 3, and all machines in the batch plant are operational. Sufficient materials equals to true, and then it gives the machine states. Now, while the AI agent we just built is fully functional and runs locally at the edge, there's still a major limitation. It only reasons over structured data, real-time signals from our OPC UA server, and product recipes from the TimescaleDB database. But what about unstructured data like maintenance records, PDFs, or Excel spreadsheets that often contain critical operational context? For example, imagine there's a scheduled maintenance task due in 8 hours. If our AI agent doesn't know about it, it might make the wrong call about whether to proceed with production or not. So in part 3, I'll show you how to build an Agentic RAG pipeline so your AI agent can bring unstructured document into its context and make more smarter, more informed decisions. Step by step, I'll show you how to design an Agentic RAG architecture that integrates context from maintenance documents alongside real-time data from your OPC UA server and TimescaleDB. Download and run a vector embedding model locally using Ollama. Store document embeddings in ChromaDB. Build semantic search functions to retrieve relevant context and expose them as tools for your industrial AI agent. Before we dive in, let me show you a quick demo of the finished project, and then we'll go through exactly how to build it. I've built a batch plant production assistant that can decide whether to proceed with production based on raw material availability, machine availability, product recipes, and maintenance schedules and potential breakdowns. For example, if I ask, I would like to produce 5 batches of product A tomorrow. Is it possible? The agent will reason through all its available tools, checking inventory, equipment status, recipes, and maintenance documents, and return a clear go or no-go decision with an explanation. Okay, let me describe our scenario here. So I have an industrial AI agent that monitors a simulated batch production facility. This agent connects to real-time equipment data through an OPC UA server endpoint, where it checks material levels in our storage tanks and verifies the operational status of our production machines. It also connects to our TimescaleDB plant database to retrieve product recipes, checking exactly how much raw material is needed to produce any given product. Using all this information together, it provides detailed responses to questions like, can we produce 50 batches of product A? However, there is a critical gap in this system. What about all the information that isn't in the real-time sensors or the structured databases? The maintenance schedules sitting in the Excel files and the calibration certificates in PDFs and so forth. This is where some of the most critical production constraints live, and our current agent is completely blind to them. And that's why we want to bring all of this data into the context of our AI agent. Now let's take a quick look at our existing AI agent code to understand our starting point. Our current setup consists of several key components. I have 2 Python scripts that handle our data access. One reads from an OPC UA server, pulling real-time information about tank levels and machine states. The second one queries our TimescaleDB for product recipes and material requirements. And then I have a tools module that takes the scripts and uses the LangChain framework to transform them into tools that our LLM can call. And then we have got the main module, and here I'm using Pydantic's base model to ensure we get consistent structured responses from our agent. For the LLM, I'm using Claude through Anthropic's API, though you could easily swap this for a local model using Ollama, as we demonstrated in a previous video. The prompt template is where we define the agent's behavior. We tell it its role, explain what tools are available, specify the output format we want, and include any special rules or constraints. Okay, so let me quickly run our program to show what our current AI agent can do. Okay, so it will prompt me to enter the number of batches that I want to produce for a given product. Okay, so as you can see, my agent has returned a decision. Say yes, production is possible. And then it explains, it comes up with the reasoning where it actually does the calculation of the amount of stuff that currently in the tanks, and also the requirements from the product recipe. And then it concludes that there is sufficient materials. And then it tells me the current status of the machines. And then it also gives me the current material availability. And then it also specifies the tools that it used. Now, when I ask it something like, can we produce 10 batches of product A tomorrow? So it still gives us the same decision, yes, production is possible tomorrow. But what if we've got a scheduled maintenance on any one of these pieces of equipment, and that information is stored in the maintenance documents? Or what if a calibration certificate is about to expire? So that's what we want to do. We want to build an agentic RAG pipeline to bring in all of this additional context from the maintenance documents. Now, before we dive into the implementation of our RAG pipeline, let me explain how agentic RAG actually works in an industrial context. First of all, there are two main approaches to implementing RAG. There is what is called naive RAG, and there is agentic RAG. You'll find out shortly what the difference is and why we're using agentic RAG. Now, currently, when I send a query to our AI agent, that query goes straight to our LLM. The LLM processes the query, looks at what tools it has available, and then it comes up with a plan for how to utilize those tools to fulfill the user's request. Now, instead of just passing the user's request directly like that, we want to utilize the information in our maintenance documents to enrich the query with additional context. And to do that, we first need to put our documents into a format that makes it easy to match what the user is asking with any relevant information in those documents. In other words, we want to enable semantic search. And here's how it works. We take each document and convert it into a vector, essentially a list of numbers that mathematically represent the meaning of the text. To create these vectors, we use a specialized machine learning model called an embedding model. This model reads text and outputs these numerical representations, which we can then store in a vector database. When a user asks a question, we also convert that question into a vector using the same embedding model. Then we can mathematically compare the question's vector with all our document vectors to find the most relevant or the most similar information. Now, here's the key difference between the two approaches. With naive RAG, every time the user asks a question, we automatically search for relevant documents and force feed that context to the LLM along with the query. It's like giving someone a stack of potentially relevant documents every time you ask them a question, whether they need them or not. With agentic RAG, and this is what we're building in this demo, we don't force the context onto the agent. Instead, we provide the RAG system as a tool that the agent can choose to use. The agent decides if and when it needs to search the maintenance documents. Okay, now let's take a quick look at our complete agentic RAG pipeline before we start building. For our demo, we have a maintenance schedule document that contains upcoming preventive maintenance dates and equipment health scores, a maintenance report with recent equipment issues, vibration data, and spare parts inventory. Now, I'm using markdown files for easy editing during the demo, but in production, this could be CSVs or PDFs or any format from your maintenance systems. For our embedding model, we have two options. We could use a Cloud API like OpenAI's embeddings, but for this demo, I'm going to show you how to run the embedding model locally. And for storing our vectors, we're using Chroma, which is an open source vector database. Okay, let's go ahead and build our demo. First, we need to download our embedding model. And for that, we're using Ollama, which is a platform that lets you download and run models locally with zero configuration. To download it, you just go to ollama.com, download it for your operating system, So I have already downloaded it on my machine. And if I open my terminal and type in Ollama, you can see that it's installed and running. And if I type in Ollama list, you can see the models I currently have. I've got Mistral and Llama, which are large language models. But for this demo, we need an embedding model specifically. So let me show you how to download one. So we go to the Ollama website and then go to models, and then you filter by embedding. So you can see there are several options here, but I'm going to use this one. So I'll copy the instructions to pull the model onto my PC. Go back to my terminal and run the instruction. Now, if I run Ollama list again, you can see that I now have my embedding model. Okay, so I'll create a new folder here. And then I'll place some documents inside the folder. Okay, so I've added 2 documents inside our maintenance docs folder. So let's go ahead and open up and see what's inside these documents. So first we've got the maintenance schedule document. So this document contains upcoming preventive maintenance dates for our reactor, mixer, filler, plus equipment health scores. And then you'll notice here that we've got special considerations for product types. For example, product A cannot be produced within 24 hours after reactor maintenance. Product B can be produced immediately after maintenance, and so on. And we also have a maintenance report document. So basically this document contains recent inspection results, vibration measurements, reliability metrics, and so forth. Okay, now let's build our Agentic RAG pipeline. So I've created a new Python module named maintenance rag.py. So this is the module that's going to be the implementation of our RAG pipeline. It will load our maintenance documents, convert them into searchable vectors, and provide tools that our AI agent can use. So let me walk you through the code. First, we import dependencies. We have LangChain utilities for loading and splitting documents. We have Chroma, our vector database that will store and search our document embeddings. And we have Ollama embeddings, which connects to the embedding model we just downloaded. Now we create our maintenance rag class. So this is where we configure the entire system. We start by setting up our 4 key parameters. First, the path to our maintenance documents folder. Second, the persistent directory for Chroma. This is where our vector database will be stored on disk so that we don't have to re-index every time. And then third, we specify whether to use local or cloud embeddings. We're going to be using local. And finally, we name our collection. So you could think of this as a table in our vector database. And then here, since our embedding model is local, we specify the name of the embedding model that we installed using Ollama. And then next comes the function for setting up our vector storage. So basically this checks if a database already exists. If it does, it loads. If not, it creates a new one. And then we've got the load and index documents function. So this is the function that is going to be doing all the loading of our documents. So here we load all markdown files from our maintenance docs folder. Each file becomes a document object that contains both the text content and metadata like the file name. Okay, now here is an important concept. So basically, long documents are problematic in the sense that for semantic search, they contain too many different topics. So we need to split them into chunks. So as you can see here, I'm splitting them into 100 character chunks with 200 character overlap. So the overlap ensures we don't lose context at chunk boundaries. So each chunk becomes a separate searchable unit, making our searches much more precise. And then finally, we use our embedding model to convert each chunk into a vector and store it in Chroma. And then in this function here, we further classify our document by tagging it with metadata. For example, is it a maintenance schedule? Is it a maintenance log? Is it a calibration certificate, and so forth? And then we've got a semantic search function. So now this is our core search engine. It takes a query, converts it into a vector, and finds the most similar document chunks. So as you can see here, I've got a parameter k equals to 4, which means that we want the 4 most relevant chunks. And we can, of course, filter by document type. Okay, now that we have loaded our documents into the vector database as embeddings, we now want to define actions that our AI agent could possibly take, or possible ways the agent could retrieve context from our documents. So we define these functions that bridge between raw document search and actionable intelligence. So instead of just retrieving text chunks, they extract specific decision critical information that the AI agent needs to determine if production can proceed or not. So here we've got the check maintenance schedule function. So as you can see here, it builds a query for checking for specific context about the maintenance schedule. And then it calls the semantic search function and provides all of this information. And then we've got the check calibration status function, and we've got the check equipment reliability function. So again, here you could see that the query involves checking the mean time between failure reliability, vibration, failure hours, recent maintenance, emergency repair, and so on. Okay, now again, since our AI agent is based on LangChain, it cannot directly call our Python functions, so we need to convert them into tools that our AI agent can use within the LangChain framework. So we need to create a mapping between the LangChain tools and these Python functions. So this is what this create maintenance tools method is doing. So basically, it creates the wrappers for our functions. And then as you can see here, it's creating a LangChain tool, specifying the tool name, mapping it to a function wrapper, whereby this function wrapper calls the actual function here. Okay, so before we continue to integrate our RAG pipeline into our AI agent, let us first test it to see it can actually retrieve all of this information for us. So as you could see here, I'm calling these functions directly and providing the product name and the date. Okay, let's go through the response to see what happened here. So as you could see here, it created a new Chroma database. You can see now we've got a new directory here for Chroma. And then it loaded 2 documents, which are the documents in our maintenance docs folder. And then it split it into 9 chunks, and then successfully indexed 9 document chunks in Chroma. And then here, this is a function where checking maintenance schedule for product A on August 16, 2025. Can proceed true, which means there's no upcoming maintenance schedule. Calibration status can produce, there's no calibration details. And then here, check equipment reliability. We've got the risk law, we can proceed. And then here under getting maintenance context, we can see that we've got the next scheduled preventive maintenance for the reactor on August 25th. Okay, so now let us proceed. Okay, so now that we've got our RAG pipeline working, I want to update my tools module to include these new RAG tools. Okay, so I've already done that. Let's go through the code here to see what we have included. So as you can see here, these were the existing tools. So we had get material availability, get machine state, get product details. And then now we're adding these new RAG tools. So first of all, we're creating an instance of our maintenance RAG class, and we're providing all of these initialization parameters. And then we're calling this create maintenance tools method, which does the mapping of our RAG functions into our LangChain tools. And then here we list all of our tools, including the RAG tools. Okay, so let's go ahead and test our tools here before we proceed to our main function. Okay, so you can see here that we're testing these tools. So we can see our material availability tool returns the material level in our tanks. And if we check here on ignition, you can see that these are the current readings. And then here we've got this tool that returns to us the states of each equipment. And then here we've got a tool that retrieves the data about a product recipe from the database. And then here we've got the RAG tools. So you can see this did a maintenance schedule check. It checked 4 documents and then it concluded that we can proceed. So again, this one, calibration status check. And since we don't have any calibration document here, there was no document to check. And then we've got equipment reliability check. So it did 5 document checks, can proceed, and the risk level is low. Okay, so now that we've built our RAG pipeline and we've integrated it as tools into our LangChain framework, now let's go ahead and go into our main program for our AI agent and see how we can then integrate this Agentic RAG pipeline. So again, here we start by doing a bunch of imports. And then here you'll notice that for the structure of our response, in addition to the decision reasoning, sufficient materials, machine states, and material availability, we have added maintenance conflicts, calibration issues, reliability concerns, and recommendations. So we want these to also be part of that response. And then for the LLM, I'm using Claude from Anthropic. So again, you need to make sure that you set your APIs in your environment variables. And then here I've updated the chat prompt template. So basically we're saying you are an advanced batch plant production assistant with access to both real-time data and maintenance documentation. Your task is to provide a comprehensive production feasibility assessment by analyzing material availability, machine operational states, maintenance schedules and conflicts, calibration status of critical equipment, equipment reliability, and spare parts availability. And then we also, provide the decision process. First, get the product recipe to understand the material requirements, check current material levels, verify all machines are operational, check maintenance schedules, verify calibration status, access equipment reliability, and so on. And we also provide production rules for each specific product. Product A cannot be produced within 24 hours after reactor maintenance, and so on and so forth. And then we also have got decision categories. Yes, all checks pass, production can proceed safely. And then we also add that we need to always provide specific reasons for your decision, quantitative data, clear recommendations for addressing any issues, and risk assessment if proceeding with warnings. Okay, and then here we get all the tools. And then we create an instance of our agent, our tool calling agent. We pass to it the LLM, the prompt, and the tools. And then from there, we instantiate the agent executor, which does the actual execution of these functions if the LLM needs those to be executed. And then here we're extracting JSON from the response. And then this is a function for printing our production assessment. Okay, let's go ahead and run our AI agent with the Agentic RAG pipeline included. Okay, as you can see, it's checking. Okay, let us see what was the final response. So here you can see the decision is yes. And we've got the reasoning here. All checks pass for producing 5 batches of product A tomorrow. Material requirement, and then it goes off and does the calculation, which shows how much we've got. All machines are operational, no maintenance conflicts, all calibrations are current, which is obviously maybe not true because we don't have a calibration document. But then again, that actually portrays the reason to really build a robust agentic pipeline, because if you ask an agent to check the calibration and it doesn't find any documents, it might start to make up things like this one. And then here, equipment reliability is good with adequate spare parts. And then here we can see it checks, it gives us the exact amount of material in our tanks. And then it tells us the machine states of each piece of equipment that we're using for production. And then we've got recommendations here: proceed with production as planned, monitor failure state as it's currently idle, consider scheduling tank refills after production run. And then here it tells us which tools it used. So it used the get product details tool, get material availability, get machine states, check maintenance schedule, and check calibration status. Now, while our AI agent can reason over structured and unstructured data, there's still a big challenge. So far, we've created tools for our agent by wrapping Python functions and mapping them as custom LangChain tools. That works fine for one agent, but what happens when another AI agent built with Google Agent Development Kit or one built with the Crew AI framework also needs access to the same OPC UA server, TimescaleDB, and maintenance documents? We would have to rebuild and remap the tools for each framework. Clearly, this approach doesn't scale, as more agents need access to the same resources. That's why in part 4, I'll show you how to build a model context protocol server. With MCP, you can standardize how industrial AI agents access data and tools. So you build the integration once and use it across any agent from any vendor without rewriting a single line of code. Step by step, I'll show you how to create Python functions that access data from an OPC UA server, convert those functions into MCP server tools that can be accessed by any AI agent regardless of the framework it's built on, and then we will test our MCP server using MCP Inspector. So in a previous video, I demonstrated how to connect a LangChain AI agent to industrial data sources such as an OPC UA server and a TimescaleDB database. This was done by manually mapping Python functions into LangChain tools. But here's the problem. If you introduce another AI agent that also needs access to the same tools, you must repeat the process by creating another set of custom connections and mappings, and a third agent, and the cycle repeats. And the result is that you have multiple AI agents accessing the same data source, but each through custom one-off integrations. So clearly this approach doesn't scale. Now, what if instead of building custom connections every time, we had a standardized server that exposed tools and data in a consistent way? That's exactly what the model context protocol does. MCP standardizes how LLM-powered AI applications connect to tools and data sources. With MCP, you can build once and use everywhere, avoiding the constant reinvention of integration logic. Now, MCP follows a client-server model, and there are three main participants in an MCP architecture. There is an MCP host, which is an AI application or agent that manages one or more clients. And then there's an MCP client, which maintains a dedicated one-on-one connection with an MCP server and retrieves context on behalf of the host. And then we've got the MCP server, which provides tools, resources, and prompts to MCP client. In short, the host can connect to multiple servers, and each client manages its own server connection. Now, the foundation of MCP is its primitives, which are essentially standardized building blocks for communication. There are server-side primitives, which is what the server exposes to the client. These consist of, number one, tools, which are executable functions that an MCP client could call, e.g. file operations, database queries, or API calls. The number two, resources, which are contextual data sources that may be of interest to any client. For example, OPC UA tags, database records, or some API responses. And then number three, prompts, which are reusable prompt templates that the client may utilize to get the best results from what the server exposes. For example, this could be system prompts or some few short examples. And then there are client-side primitives, which is what the clients expose to servers. And these consist of things like sampling. Now, because you don't want to tie an MCP server to a specific LLM, the MCP server needs to be able to utilize whatever LLM the client is using to request some model completions or request services of the LLM. For example, an SQL Access MCP server can ask the client to generate queries from natural language while staying model agnostic. There is elicitation, whereby servers can request more input or confirmation from end users. And there's also logging, where servers can push log messages to clients for monitoring and debugging. Now, finally, MCP supports two transport options: standard input-output transport for local process-to-process communication, and HTTP transport, which uses HTTP post for requests, and then optionally HTTP server-sent events for streaming responses. Now, in our demo, we will build an MCP server that wraps around our OPC UA server. The server will allow agents to interact with it consistently without the need for repetitive custom integrations. Okay, so let's go ahead and start building our MCP server to enable AI agents to access industrial data. Specifically, we're going to expose OPC UA server data through MCP. So let me show you what I've got running right now. I have a Python script that acts as an OPC UA client and is connected to an OPC UA server that's running my simulated batch plant. So if I quickly pull up my ignition SCADA here, you can see the visualization of my batch process. There's all the equipment with their current sensor values updating in real time. So let's quickly walk through what this Python script does. So here I'm configuring my OPC UA server endpoint and the tag IDs for the OPC UA data points that I'll be accessing. And then here I've got an enum class to convert all my machine states into descriptions. And then here I'm creating the batch plant client. But more importantly, I've got these two functions: get material availability, which is basically a function that reads the tank levels and tells us how much material we have available in each tank for production. And then secondly, we've got this get machine states function, which basically reads the current operational states of all my machines. So let's go ahead and run the script to see what it does. So as you can see, if I run this main method here, which calls the get material availability and the machine states, it returns the current values of the tank levels, and then it also returns the current states of my machine. So if I open up my SCADA system here, you can see this is the current values that I'm reading. So this is all through an OPC UA server using the OPC UA client. So what we want to do now is we want to take these OPC UA data access functions and transform them into MCP tools. This way, AI agents can access them in a standardized manner. We're going to use the first MCP Python package, which gives us a high-level interface for building MCP servers. And then we will test everything using the MCP inspector. Okay, so first things first, let's get our dependencies sorted out. So I'm going to use a package manager called UV. So if you don't already have it on your machine, go ahead and install this package. Okay, so once you have UV package installed, we can go ahead and initialize our project. We do that using the UV init command. And then next, we want to create a virtual environment. Okay, next we need to add a couple of packages to our requirements.txt file. So here we've got the async UA, which is the package that we're currently using to turn our Python program into an OPC UA client. And then here we're going to add the MCP package. So let's go ahead and install these dependencies in our virtual environment. Okay, so now that we've got the necessary packages, let's go back to our Python script and start building our MCP server. Let us start by importing the MCP server. Next, we initialize our MCP server. And I'll give it a name. Okay, so we've initialized our server. The next thing that we want to do is to define our Python functions as MCP tools. And doing that is as easy as decorating our functions with the MCP tool. And then we will do the same for the other function. So what I've done now is I have defined two tools, on our MCP server, the get material availability tool and the get machine states tool. Now we need to actually run the server. So I'll get rid of this. And then I'll specify the transport as standard input output. Okay, so now we've got our MCP server, and now we need to go ahead and run it and test it using MCP Inspector, which is a browser-based environment that allows us to explore our MCP tools, resources, prompts, and everything else that our MCP server provides. So to start the MCP server and run it, I'll use this command. Okay, so as you can see, our MCP server is running and we have automatically started our MCP inspector. So already you can see this is the Python script that's running the MCP server. And then here, if I go ahead and click on connect. So here we can go under tools and then we can say list tools. And then you can see here, this is where our functions or our tools start to appear. Get material availability and get machine states. So if I click on get material availability, so you see this is the tool, this is the output schema for the tool. If I run the tool, you see that we actually get the values from our tank levels. If I open up my ignition, you see this is the same value that we're getting here. And then if I go to machine states and run the tool, you see we actually get the current state of all my equipment. Now here we're only exposing the tools via MCP server, but you can then go on to extend with things like resources and also prompts. So we've successfully built an MCP server and tested it using MCP Inspector. Now with our MCP server, we've solved a key challenge, giving AI agents standardized access to industrial data through reusable tools. But there's still one more challenge ahead. What if we have multiple AI agents in our system, not only needing access to tools, but also needing to communicate and exchange information with each other in a standardized way? That's where the agent-to-agent or A2A communication protocol comes in. So in part 5, I'll show you how to build a multi-agent industrial AI system and implement the A2A protocol to enable seamless communication and collaboration among your AI agents. Step by step, I'll show you how to break down a monolithic AI agent into multiple specialized AI agents, implement the A2A communication protocol, and standardize the way your agents exchange data and collaborate. Before we dive in, let me show you a quick demo of the finished project, and then we'll go through exactly how to build that. So I've built 3 AI agents, an equipment monitoring agent, a material calculating agent, and an orchestrator agent. Each AI agent implements the A2A protocol, and I also have a user-facing application that acts as an A2A client. With this setup, I can interact directly with the equipment monitoring or material calculating agents, or send a query to the orchestrator, which delegates tasks to the other agents and returns consolidated result. All of this happens through standardized communication with the A2A protocol. Okay, so let me quickly describe our demo scenario for this tutorial. So we're running a simulated batch plant that mirrors a real facility, 3 storage tanks for raw materials, a mixer to combine them per recipe, a reactor for the chemical process, and a filler that packages the finished product. All real-time signals from the production equipment are exposed through an OPC UA server. In a previous video, we built a single industrial AI agent that monitored this plant. It read live data from the OPC UA endpoint to check tank levels, machine statuses, and it queried TimescaleDB database for product recipes to calculate raw material requirements and then be able to answer questions like, can we produce X batches of a given product? Now, instead of relying on one monolithic agent, we're decomposing the work into a multi-agent system. Instead of one agent doing everything, we're creating 3 specialized agents. First, an equipment monitoring agent that specializes in real-time data. It connects to our OPC UA server and knows everything about tank levels, machine states, and operational statuses. Second, a material calculating agent that specializes in product knowledge. It connects to our TimescaleDB database and knows all about product recipes, material requirements, and batch calculations. And third, an orchestrator agent that coordinates the other two. When you ask about production feasibility, the orchestrator knows which specialist to consult, how to combine their insights, and how to make the final decision. Now, these agents don't need to know each other's internal implementation. They communicate through agent-to-agent or A2A protocol using standardized messages. Let me briefly explain how Google A2A works so that you have the relevant context to follow along this demo. The agent-to-agent protocol, or A2A, is a standardized framework that enables AI agents from different vendors using different models built with different frameworks to communicate and collaborate seamlessly. Think of it as a universal language for AI agents. Without A2A, if you have agents built with LangChain, AutoGen, and CrewAI, they can't semantically interoperate with each other. Each uses its own communication format. A2A provides the common language they all understand. A2A follows a request-response model similar to how web APIs work. A client agent sends a request and a server agent responds. Now here's the interesting part. Any agent can be both a client and a server. So your equipment monitoring agent serves data when asked, but it might also need to request information from other agents. The protocol defines 5 core capabilities. First, standardized message formats. All communication uses JSON RPC 2.0 over standard protocols like HTTP or gRPC. This means agents exchange structured, typed data that any system can understand. Second, dynamic discovery through agent cards. So each agent publishes an agent card, which is like a business card that says, I'm the equipment monitoring agent, I can provide tank levels and machine states, and here's how to reach me. Other agents can discover these cards and automatically know what capabilities and skills are available from what agent. And then third, it has got built-in task management. A2A includes task orchestration, so agents can say, I'm working on it, and provide updates as they progress. And then fourth, multi-modal data exchange. Agents aren't limited to text, they can exchange sensor data, graphs, maintenance reports, even video feeds from inspection cameras. And then lastly, security and asynchronous communication. A2A includes encryption for sensitive industrial data and supports real-time streaming updates using server-sent events. Okay, so now that you've got a brief understanding of what A2A is all about, let's go ahead and look at our multi-agent industrial AI architecture based on A2A. When a user asks, can we produce 4 batches of product A? The request goes to our orchestrator agent, which exposes an A2A server endpoint. The orchestrator maintains an agent registry listing all agents it can reach via A2A. Using this registry, it discovers each agent's capabilities by reading their agent cards from a well-known endpoint. So it knows the equipment monitoring agent can provide material availability and machine status information. It knows the material calculating agent can provide production requirements. The orchestrator delegates tasks based on what's needed. It might ask the material calculating agent what materials are needed for 50 batches of product B. Simultaneously, it asks the equipment monitoring agent what are the current tank levels and machine states. Each of our AI agents exposes an A2A server endpoint, and so to talk to those agents, the orchestrator also runs its own A2A client connections. The equipment monitoring agent connects to an OPC UA server and retrieves real-time data, while the material calculating agent queries the database and calculates requirements. They respond to the orchestrator with structured data through A2A. The orchestrator combines these insights, applies business logic, and provides the final answer to the user. Okay, so let's start with the big picture of our project structure here. So at the root level, we have our main A2A project folder. And then inside it here, you see we've got 3 key different directories. So we've got the agents directory. So this is where our AI agents live. And then we've got the app directory. This is the application layer that users interact with. And then we've got the shared directory. This is what we have as our common resources and the A2A protocol implementation. And then here we've got our environment configuration and the requirement files for our required Python packages. Okay, so let's unpack our code starting with the shared directory. So here we've got the models folder, which contains our A2A data models. So basically our models here define the data structures as per the A2A specification that all our AI agents use to communicate in a standard manner. So if we open up the agent.py module, so this module is a definition of how an A2A compliant agent should represent itself and announce itself in the A2A ecosystem. So as you can see here, it includes a class for agent capabilities, which define how an agent should represent its capabilities. So as you can see here, we've got the streaming property. So here it is used to indicate whether an agent is able to handle streaming or not, and then push notifications and then state transaction history. And then we've got another class that defines the metadata about the agent skills. So basically an agent skill is what the agent is capable of doing. So as you can see, this class includes the ID, the name of the agent, the description of that agent, and then the tags, optional tags to categorize what the agent can do. So in this case, the name, the ID could be provide material availability, and then the name could be provide current material availability, description, and then examples of how these agents could be queried, right? And then you have got the input modes and the output modes, so whether it supports JSON, text, or whatever modalities it supports. And then we've also got the agent card. So this is what we spoke about earlier. The agent card is like the business card that describes the agent's capabilities. So when the agent first connects or first accesses the registry, it will get the URL where it can then start interacting with the AI agent. So the agent card contains all of that information. It contains the name of the agent, the description, the URL, where it is reachable, and the version, which is 1.0.0, and it also lists its capabilities, which are these agent capabilities here, and then it also lists the skills, which are the skills defined here. And then let's move on to the JSON RPC module. So this code here defines the best classes and structures for JSON RPC 2.0 messaging, which is the underlying protocol that A2A uses for communication. So here this includes the JSON RPC message, and then we've got a JSON RPC request, what it should look like. We've got the JSON RPC error, JSON RPC response, and we've got the internal error. And then we've got the request models. So this module defines the structured request models used in the A2A protocol. So these models basically represent the different kind of requests an agent might send or receive. So this includes sending a task or receiving a task. And this is all adhering to the JSON RPC 2.0 format. So as you can see here, this includes a class for sending a task request, a class for sending getting a task request, and then you have got an adapter, and then we've got a send task response, and then get task response. And then finally under modules here, we've got a task. So this is the module that defines all the task related modules used in the A2A protocol. So primarily in our demo, we're using tasks as a way to exchange messages between all these multiple AI agents. So here we've got a definition of all those task related models. So here we've got a text part, which is basically represents a part of a message that goes along with the task. And then here I've got a representation of a message, and then the task status, and then the actual task parameters, and then the task send parameters. And then here I've got an enum type that holds all the different task states from submitted, working, input required, completed, cancelled, failed, or unknown. Okay, so now let's go into the A2A folder. So basically this folder contains our implementation of Google's agent-to-agent protocol. So here I've got the agent registry. So basically this is where every AI agent that joins that A2A network or ecosystem needs to register themselves. So this could be hosted in the cloud or whatever registry you're using. So in this case, we're using this file basically to list our AI agents. So this one is our equipment monitoring agent, and then this one is our material calculating agent. So we've got two agents registered here in this registry. So basically, the registration here, you are specifying the host name of that particular agent. So as you will see later, an AI agent will use this host name to then append that well-known address where it can then be able to access the agent's card, which lists all the capabilities, the skills, and the URL where the agent can then be able to interact with that specific agent via A2A. And then just here we have got the discovery module. So basically, again, this is a shared utility module that any AI agents, any of our AI agents here can use to discover the capabilities of the other agents. So basically, as you can see here, it is accessing that registry. And then once it does that, it loads the registry and then it pulls those agent cards. So it will list the agent cards of all the AI agents that are registered in our agent registry. And then here we've got the client module. So basically this defines a Python client for interacting with an A2A server. So here basically, as you can see, we've got an A2A client error, A2A client JSON error. So and then here we've got the main interface of the A2A client. And then here we've got a method of how our A2A client can send tasks to the server. It can get tasks and it could send a request. And then here we've got the server. So again, this is also a simple A2A server implementation that our AI agents would then be able to also use to implement A2A server. So it supports, again, the ability to be able to start a server, get agent cards, handle requests, create a response. And then finally, in our A2A directory here, we've got a task manager. So basically, this module defines how tasks are managed in an A2A protocol. So as you'll see later here, again, we're going to use each of our agents is going to implement this class task manager or in-memory task manager to be able to provide that bridge between the Google A2A tasks and the actual execution by the agent. So again, here it defines how to upset a task, on send task, what should happen, and then on get task, what should happen. Okay, now let's have a look at the code for the actual agent. So if we go here, you see we've got the equipment monitoring agent, material calculating agent, and then we've got our orchestrator agent. So if I open this equipment monitoring agent here, so here we've got the main Python function. So basically this is the function that is responsible for starting our equipment monitoring agent. It runs it as an A2A server at port 002. And then here we instantiate the agent card. We specify what the skills this agent is capable of. So as you can see here, this is a material availability and material states ID. This is a tool for providing material availability and machine states. The description, it replies with material availability and machine states. And then we've got the text, and then here are examples of how this tool could be used. So what is the current material availability in tanks and the status of production? Or it could be give me the status of production equipment and material availability. So this is what the AI agent that discovers this agent card is going to see and then know exactly how it could use this AI agent. And then here we've got the agent card that then puts together all the skills, capabilities, and all this information about the AI agent, and then we start the server. And then here we've got the actual AI agent code. So maybe before we look into that one, first of all, let's look at this module, which is an OPC UA data access. So these are basic Python functions for reading an OPC UA server. So again, here you see I've got the server endpoint, and then here I've got the node IDs for all the tank levels that I want to read, and then the machine statuses that I want to be able to read. And then I've got an enumeration type here to determine the machine states. And then here I've got a class for an OPC UA client. And then I've got these methods, basically, which is get material availability, which is basically an OPC UA request to get the material availability using those node IDs. and then we've got get machine states, which is again an OPC UA request to get the machine state using those node IDs. So what we're doing is basically we're taking these Python functions and then we're mapping these to LangChain tools. So we're using LangChain as the framework for this specific AI agent. So again, so this module is responsible for mapping those tools. As you can see here, I'm importing these two methods from our OPC UA data access module. And then here I'm specifying this as a get material availability tool, which is mapped to this specific function, get machine states tool, which is then mapped to this function. So we've defined our data access layer, we have mapped those two tools, and then now we go into our main AI agent. So again, as I mentioned, this is a LangChain AI agent. So as you can see, we're doing a bunch of LangChain imports here. And then this is specifically a tool calling agent that we are importing here. And then first of all, here we're loading our environment variables, which include the API key for our Claude LLM model. And then here we are using this, we're creating a model of the response. So our response, we expect it to be structured in this way. It should contain the machine states, material availability, and the tools used. And then from there, we create a class for our equipment monitoring agent. We specify the supported types, and then we initialize this AI agent with the name of the model. And then here we specify that this is a chat anthropic model. And then here we sort of like set that pydantic output parser as the structure of the output that we want to be able to provide as a response. And then here we create the prompt template, which you're going to see down here shortly. And then here we define the tools that this AI agent is able to use. So again, you see we've got the get material availability tool and get machine states tool, which are the tools that we have imported here from our LangChain tool. So from the equipment monitoring agents, from the tools here, these are the tools that we mapped from our OPC UA functions. And then we come here, we then define our prompt template, which is the main instructions for our agent here. So basically we're saying you are a batch plant monitoring assistant. Your task is to respond with the material availability and the operational states of machines in our batch plant. To make this determination, you need to check current material availability in all the tanks and then check machine states. Always be specific which materials are available in what quantities and in which tanks, which machines are operational or faulty, and then your response must only be JSON. So by giving it this instruction, automatically the LLM will know which tools it needs for which specific request. And then here, because we want to format this in a JSON format, we grab that response that the LLM provides and then we structure it into a JSON. And then this is the function that is invoked by our task manager. So we've got a task manager here. So the task manager is the one that interfaces with the A2A protocol. So whenever a task is sent to this specific AI agent, the task manager is the one that determines, sort of like provides that bridge to then invoke this AI agent here to get the response and then act as an intermediary. So let's jump into the task manager here and see how it does that. So again, here we've got a task manager. So our task manager, again, here you see it implements this in-memory task manager. So basically it gets a user query. So if a user sort of like sends a message directly to this agent, it will get the query, extract this query here, and then here on send task, right? So this is the logic for handling a task. And then here it will invoke this LangChain agent, that invoke method of the LangChain agent, and then it grabs the result into this text, and then it provides that as the response using the A2A protocol. So this acts as an interface between our A2A protocol and the actual execution of our LangChain agent. Okay, so this is pretty much the same that we're doing for the material calculating agent. As you can see, it's got a main entry function, it's got an agent. Again, this is a LangChain agent, and basically this one, the tools here are basically a connection to the database. So we've got a database access file here, which is again a basic Python script that, performs this query, select so much. So after being given a product name, it will go into the database, then calculate, get the product recipes, raw materials, the products, and then returns all of that information. So here it returns the material name, tank number, and the quantity of the product. So we've got a tools module here, again, that maps these database data access tools into a LangChain tools. And then if we go into our main agent file here, this is where we then create this tool calling agent, and then we import these get product tools, these LangChain tools, as the tools for this agent. Again, here we define the structure of the response. So we want the material requirements, and then we also want to know what tools were used. And then we create a class for our material calculating agent. Again, we do the same initialization. And then here, this is the prompt template. So again, here we're specifying you are a batch plant production assistant. Your task is to calculate the amount of material that is required to produce a specified number of batches. And then we let it know how it needs to sort of like, do that calculation. First, get the product details to understand material requirements to produce a batch. Using that information and the number of batches we want to produce, calculate the total requirements, provide a clear response, and then we give it instructions about what it needs to be specific about. And then we do the same thing. We extract the JSON payload, and then we've got this invoke function that is then called by its task manager. So each agent has got its own task manager module, which is an implementation of the task manager that we created under the shared models. And then from there, we've got this main function. Right, and then we've got the orchestrator agent. So the orchestrator agent, as you can see, is slightly different because it does not have direct connection to the tools. Instead, these two other agents are its tools. So here again, it's also got a main entry function. It runs on port 4003. The material calculation agent, by the way, it runs on port 4003, and then this one runs on port 004. And then we've got an agent connect module. So basically, this is an agent. This is a module that allows this orchestrator agent to be able to connect to the registry, sort of like to discover what AI agents have registered themselves and then know about this capability. So like any agent can do this. The equipment monitoring agent can also be able to discover all the other agents, including the orchestrator agent. But for this demo, we're using the orchestrator agent as the only one that is has got the ability to discover what AI agents have been registered. So it uses what is called an agent connector, right? And then it's able to send tasks to those AI agents using this payload, which is, if you notice here, it's actually an RPC message format. It's a JSON RPC 2.0 message format that includes an ID, session ID, and message. And then we go into our main AI agent here, which is the orchestrator agent. And then here, because this is the AI agent that we want to sort of like interface with the user, we want to know the final decision on whether, if we ask if we should proceed with production, it should let us know what this decision is. What is the reasoning behind this decision? Let us know if there are sufficient materials or not. It must give us a list of the machine state so that we can verify that it actually arrived at a very correct decision. It also needs to let us know what materials are available, and it needs to specify what tools it used. So again, you will notice that it is using the same Claude LLM as our sort of like brains of this agent. And then it has got a prompt template, and then it has got tools that are then assigned to it here, including the LLM and the prompt. And then if we go to our create tools here, so basically these are the tools. So if you notice on the other two agents, we've got a separate module for the tools, but here for the tools, we're using this list agents, which is what it gets from the tool connector. So from this agent connect, it connects, and then it gets a list of agents, and then it lists those agents as tools here within the AI agent itself. And then here I've got a prompt template. So basically, we're telling this that you are an orchestra agent for batch planning. Your job is to determine if the plant can produce a specified number of batches for a given product. right? And then here we say always use delegate task tool twice to gather information. First, delegate to material calculating agent to calculate material requirements. Second, delegate to equipment monitoring agent to check material availability. And then format the delegate tasks, and then we specify how you should format that information. After receiving response from both agents, analyze the data and make a decision. Your final output must be only a valid JSON object. And then we specify, we give it an example here on how you should sort of like format that response. And then we tell it what not to include. And then this is the function for, delegating the tasks. So this is the specific function that allows this AI agent to be able to call these tools when and if it deems fit to do so. And then we extract JSON from text. So these are all the different functions that are, acting as a fail-safe mechanism for this specific AI agent. And then here, most importantly, we've got this invoke function, which runs this AI agent. And then here, the task manager is actually in this module as a class. So as you can see, this class, we've got the orchestra task manager, which is pretty much an implementation that is more or less similar to what the task manager of the standalone AI agents, equipment monitoring, and the material calculating. So basically, again, here we're checking the status, the health status of the AI agents, and then we're getting the user text. On send task, this is what needs to happen. Let's finally look at our app. So basically, our app is a command line interface. When it starts up, it simply prompts the user, how can I help you? And then it strips that, query, and then it sends that as a JSON RPC message to whatever server you point it to. So when it starts up, when you run this agent, you're going to specify which server it needs to point to. But by default, it will fall on this. So for the demo, we're actually going to manually point it to the different AI agents that we want to send the message to. Okay, so this is our code for our multi-agent system. Now let's go ahead and see the demo. Okay, so I've got my AI agents set up here and ready to run. So here I've got my equipment monitoring agent, which is an AI agent that monitors the availability of materials in all of our 3 tanks. It also checks the states of our production machines. And then here I've got a material calculating agent, which is an AI agent that accesses our database and pulls out the product recipes and checks how much material is required to produce a certain number of batches of a given product. And then here I've got the orchestrator agent. So this is the AI agent that delegates tasks to the equipment monitoring agent and the material calculating agent based on what the user is requesting. Okay, so I'll go ahead and run my equipment monitoring agent. Okay, so as you can see, my equipment monitoring agent is running at port 40002. Now I'll go ahead and run my material calculating agent. Okay, my material calculating agent is now running at port 40003. And then I'll run the orchestrator agent. Okay, now what has happened here is that the orchestrator agent is running and it has discovered these 2 AI agents using the A2A agent card. So it now knows the capabilities and skills of these 2 AI agents. Okay, and then the last one is my user facing application. So this is also an A2A client. Now, as you can see here, I can specify which A2A server I want this user client to connect to. So I'll go ahead and start by connecting to the equipment monitoring agent directly. Okay, so now I'm going to ask, what is the material availability and the states of machines in our plant? Now, when I do that, you notice that this message is now packaged as a JSON RPC request, and it is sent to the equipment monitoring agent. Now, as you can see the response where it says, the agent says, and then it gives me a JSON that says the mixer state is running, reactor state is running, filler state is idle, and then it gives me the material quantities for the tank levels, tank level 1, tank level 2, and tank level 3. So these are all available via an OPC UA server, which is exposed as a tool using the LangChain framework. Now I want to point it to the material calculating agent. So I'll direct it to port 40003. And then here I'll ask a question like, how much material do I need to produce 5 batches of product A? And then again, it packages that into a JSON RPC request and then sends that to the material calculating agent, which receives it and then it responds. So as you can see here, it says material requirements. It calculates the material 1. This is how much is needed, 4,500. For material 2, this is how much is needed. That is how much is needed. And then it also specifies the tools that it used to get that information. Okay, so now you can see these AI agents exchanging messages using the A2A protocol. And then now I'm going to connect it to the orchestrator AI agent, which is running at port 40004. Okay, now to the orchestra agent, now I can ask a question like, can I produce 4 batches of product A? Now, the orchestrator agent will take this query and then it has got instructions on exactly how to make a determination of whether one can proceed with production or not. So it will ask the material calculating agent to tell us how much material is needed, and then it will ask the equipment monitoring agent on what material is available and which machines are down. And then from there, it will do a calculation and give us a go or no go indication. So when I do that, you'll notice that the orchestrator is now calling these 2 AI agents. Okay, so we've got a timeout on the client application, but let's analyze the response from the orchestrator agent. As you can see, the orchestrator agent now has responded with a decision to say yes, and then it's got the reasoning here that says, based on the data from the child agents, there are sufficient materials in all tanks and the required equipment is operational. And then it tells us what are the material requirements, and then these are well below tank levels, tank 1, tank 2, tank 3. All essential machines are either running or idle and ready for use. So the answer here is sufficient materials true. Machine state, it tells us the machine states, and then it gives us the response. Okay, so for some reason, the client application was waiting too long to get the answer, and then it timed out. So I didn't put a long enough timeout. So let's give it another go to show you what the response looks like on the user side. Okay, so now as you can see, our user-facing application didn't time out, so we got the response from the orchestrator agent. So as you can see, the response there, it says decision yes, and the reasoning, based on the data from child agents, we have sufficient material and operational equipment. Material requirements for 4 batches are well within current availability, and all critical machines are either running or idle, which means they're ready to use. And we've got sufficient materials, true machine states, and then kind of like list the states of the machine, and then list the material availability, and then it specifies which tools were used. So if you notice here, the material calculating agent and the equipment monitoring agent are listed as tools that have been used by this orchestrating agent. So now we've successfully built a multi-agent ecosystem of AI agents that exchange information using A2A protocol. And that brings us to the end of this 5-part series on building agentic AI for industrial systems. I hope this has given you the knowledge and inspiration to start building your own industrial AI agents. If you found it helpful, make sure to like, share, and subscribe, and stay tuned for more tutorials on industrial data and AI right here on this channel. See you in the next one.